Hello, and welcome to another IsoDec tutorial video. My name is John Pavek, and today I will be walking you through basically some basic scripting for accessing and running IsoDec from within a Python script. So the file we're going to be working with is this raw file that only contains one spectrum. All we're starting with is the file path here. So the first thing we need to be able to do is actually access the data in that file. So we've got to load our importer. Import the importer factory. So this importer factory.create importer method is going to create us an importer that is specific to whatever data type we are loading. And if it's a supported data type, this should all work. And then to load our spectrum, we're going to go grab centroid data. We want to load scan1. So grabbing centroid data will automatically centroid the spectrum when loading it if it's not already centroided. So we have to have centroided data to work with that in IsoDec. So the next thing we're going to do is import the IsoDec runtime. Import IsoDec runtime. So this is actually what's going to be like allowing you to run IsoDec. So we're going to call this engine or eng IsoDec runtime. This is also where we're going to set the phase resolution, which determines which charge prediction model, either the 4-bin or 8-bin, will be used for charge prediction in this case. We're going to use the 8-bin model. Associated with this IsoDec runtime is the IsoDec config, which stores all of the parameters that control how IsoDec runs. A lot of these are just to kind of like monitor what's going on while it's running, but these are our various kind of filtering and matching parameters for how IsoDec will actually run. Most of these are kind of explained in more detail in the SI of our manuscript, but I'll kind of mention some of the important ones and then we'll adjust one just to show how that's done. So cosine similarity score threshold is important. That basically determines how well experimental data must match a theoretical isotope distribution to be accepted. Knockdown rounds, that controls how deep into the spectrum you're going to dig. And then min area covered basically determines what fraction of the experimental encoded data has to be matched to a theoretical isotope distribution for that envelope to be accepted. This parameter can be particularly helpful in the case of noisy data. So in this case, we're just going to update the knockdown rounds and go extra deep into the spectrum. So eng.config.knockdown rounds equals 10. Default is 5. We're going to run 10 and get a little extra depth on this spectrum. And then to actually process the spectrum, we're going to do eng.batch process spectrum and then specify that this is already centroided data because we loaded centroided data. So running batch process spectrum is going to populate another class associated with the runtime, which is this match collection class. So this is basically storing all of the deconvolution results for that particular spectrum, or if you're processing like a larger LCMS file, it's going to contain all of the deconvolution information for every deconvolved peak. So within this matched collection, the kind of most interesting and most noteworthy is this list of peaks. So each of those peaks is one of these matched peak objects. So each matched peak corresponds to one individual deconvolved envelope that has passed our filtering criteria. So we've got the M over Z, we've got the Z, we've got the theoretical isotope distribution, then we have the monoisotopic mass. A lot of this is kind of more advanced and there to help us track where in the original spectrum these envelopes are actually being matched. But the monoiso is the best scoring monoisotopic mass. And then we also have a list of monoisos. And basically that is the list of all of the monoisotopic masses that passed our filtering criteria. So basically the idea is if you don't want to just kind of like blanket allow n missed monoisotopics, you can just use monoisos instead of blanket allowing however many missed monoisotopics errors you want, because you know that everything in this monoisos list will be a monoisotopic mass that has solid experimental evidence in the data. So we'll also show how to plot these peaks. So we're going to have to import this. Import from IsoDec.plots, plot peaks. So our peaks are eng.peaks, centroids equals spectrum, centroid color is black. We're going to plot our peaks in blue. And we don't just yet want it to plot the masses. We're also going to import matplotlib pyplot, and we should be good to go. Actually, one more thing we'll add. A print of how many peaks we get out. So it can be a little bit confusing accessing this. So eng.pks is the matched collection, and then that matched collection, as we looked at earlier, has a list of peaks, each of which is a matched peak. So don't get those two confused when you're working with that. So we should see however many peaks were accepted in deconvoluting the spectrum there. So let's run. So we're seeing 1,400 peaks deconvolved, 1,400 envelopes deconvolved in this spectrum. We're seeing a bunch of these warning masses very high. That's associated with our neural net for predicting isotope distributions. It's been trained up to 60 kilodaltons, so anything above that will throw an error when we try to predict it. But now we can look into the envelopes that were actually deconvolved. So the top is the experimental centroids. The bottom is our theoretical matched distributions. So we can see these generally look quite good. Zoom in here. Looks like we're matching a lot of kind of what looks like kind of garbage, but actually looks like pretty good matches. So let's say you're only interested in a particular MZ range. Let's say we are interested in 1000 to 1020. equals as UD. And then the original data is spectrum. New min should be MZ range 0. New max is MZ range 1. And now since we're only processing this small window, let's reduce to 5 knockdown rounds. That should be more than enough. And now we can see we get only a small range of this spectrum deconvolved. And then one more thing we can do is also plot the masses, so we can get a deconvolved mass distribution, and that will plot alongside our plot of the M over Z distribution. So yeah, we see we've got kind of a few different clusters. So this isn't just like individual deconvolved monoisotopic masses. This is actually the mass distribution from that spectrum. So like each isotope peak is plotted with its particular mass in this spectrum, which can be interesting and worth looking into. So I appreciate you checking this out. I hope this was helpful. And this script will be stored as part of the public scripts IsoDec folder in the future. So if you would like to use it, you certainly can. Thanks.